Frequency modulation, FM synthesis, is an exciting topic. With a few simple operations, we can create complex sounds that can instantaneously change in timbre with a few simple coefficient changes. How does it work? How to control it to produce musical notes? And what you need to know to implement it. We will explore all that in this single video. Hi everyone, my name is Jan Wilczek from WolfSound.com, and if you're new to this channel, here you can learn how to process sound using self-written software. And a part of sound processing is generating sound, which is the task of sound synthesis. After having explored wavetable synthesis, the time has come to explain frequency modulation synthesis. Let's start with a brief word of history to give credit to people's hard work. The original publication on FM synthesis came from John Chowning in 1973. Because of the lack of interest of American manufacturers in using the technique in hardware synths, Chowning turned to Japan-based manufacturer Yamaha in the same year. However, it wasn't until 1983 when the first widely successful FM synth was introduced, namely Yamaha DX7. It took the market by storm and spawned a host of FM-based hardware synths. That 10-year gap between the publication and implementation should tell you how much engineering effort was required to make FM commercially usable. Before we delve into the frequency modulation synthesis, we should consider what is vibrato. Vibrato is an effect of a sound varying up and down in pitch. In other words, vibrato is a periodical pitch variation. In this sense, we modulate the pitch. To achieve the vibrato, the modulation must be quite slow, in the range of 5 to 14 Hz. Note that this range is below the human hearing range, which is typically associated with the 20 to 20,000 Hz range. Here is how a single musical note, a sign representing the MIDI note 57, sounds without the vibrato. Here's how the same note sounds when we apply a 6 Hz vibrato that changes the pitch up and down by 12 Hz. It turns out that if we increase the vibrato frequency and the range over which we change the pitch, we stop hearing a variation in pitch and start hearing a completely different timbre. Here's what happens when we increase the modulation frequency to 50 Hz and sweep the pitch up and down by 100 Hz. As you could hear, the vibrato impression disappears and we hear a completely different timbre altogether. That is the basis of frequency modulation synthesis. Let's now consider a basic frequency modulation instrument. In FM, we modulate the frequency of a carrier waveform. It means that the instantaneous frequency of the waveform's frequency at a particular time instant, is constantly being changed by a modulator, another waveform, in a regular periodic fashion. In the simplest FM setup, a sine modulator modulates a sine carrier. In this scenario, the output signal's instantaneous frequency f of t, which is a function of time, is given by the following formula. F of t equals fc plus am times cosine of 2 pi fmt. Here, fc is the frequency of the carrier in Hertz, the carrier frequency. Am is the amplitude of the modulator, which is unitless. Cos is the cosine function. Fm is the frequency of the modulator in Hertz, the modulation frequency, and t is time in seconds. To create a sine oscillator whose frequency changes according to this equation, we cannot simply put it into the sine formula like this, because it's not mathematically correct. Here, AC stands for the carrier amplitude, by the way. If you would apply the thing in this equation to generate a sound, then we would get a signal that sounds like this. Instead, we need to use the fact that angular frequency is the derivative of phase. Here, 2 pi f of t is the instantaneous angular frequency in radians per sample. Phi of t denotes the instantaneous phase at time instant t, and d over dt denotes the derivative of a function over time. Just as a side note, if you don't know what a derivative is, it is a measure of how much a given function changes at every point in time. The derivative is also a function. If you think about this equation, it makes total sense. If the phase changes rapidly, the derivative is large and the frequency is high. If the phase changes slowly, the derivative is small and the frequency is low. Back to our discussion on proper FM formula. The argument of a sine function is the phase, not the frequency. In order to obtain the phase from the equation for frequency, we must perform an operation that is inverse to derivation, namely integration. Now we can plug the formula for the phase as the argument of a sine function. This is the correct formula for a simple FM instrument. We have a sine carrier with amplitude AC and frequency FC, and the sine modulator, represented by the cosine, with amplitude AM and frequency FM. Note that we need to use a different symbol for time than t in the integral because t denotes the time point at which we compute the phase. I chose tau. FM variants are most often explained on the basis of diagrams. The diagrams can easily show how the interconnection between the oscillators are placed, much like in graphical audio programming languages like MaxMSP or Pure Data. Here is a diagram of a simple FM instrument. Each box with a sine symbol inside is an oscillator. The plus in a circle denotes sample-wise signal summation. Although FM synthesis timbres sound quite complex, their spectrum structure is very straightforward. The partials are centered around the carrier frequency Fc and spaced by the modulator frequency FM. You can see exactly how it looks in the frequency domain in this figure. In the middle, there's the carrier frequency, and on its sides are the sidebands. In general, the frequency of each partial Fp fulfills the following condition. Fp equals Fc plus k times Fm, where Fc is the carrier frequency in Hertz, Fm is the modulator frequency in Hertz, and k is any integer. That's what k in z means. To avoid confusion, let me just quickly define partials, harmonics, and overtones. Various sources use various definitions, but I rely on a distinct meaning of each of these terms. A partial is a spectrum member. A harmonic is a member of a harmonic spectrum, i.e. spectrum whose partials are in a mathematical relation to each other. For example, in a sawtooth, harmonics are integer multiples of the fundamental frequency. An overtone is a harmonic that is not the fundamental frequency. The first harmonic is the fundamental frequency. The second harmonic is the first overtone. Acoustic instrument spectra often consists of harmonic partials, inharmonic partials, and noise. One of the goals of FM synthesis research was to be able to use a MIDI keyboard to control it. That means we need a way of keeping the timbre somewhat constant while changing the pitch. It turns out that if the ratio of the carrier frequency to the modulation frequency is constant, the partials structure is preserved. In other words, if we multiply the carrier frequency by some real constant, we need to multiply the modulation frequency by the same constant in order to keep the partial structure intact. The frequency ratio is sometimes denoted C to M or RF. If Fc and Fm change but their ratio RF doesn't, then the timbre shouldn't change either. There are various recipes for RF to create different timbres. You'll hear more examples later on in the video. Let's look at an example. From now on, you can assume that AC equals 1 because changing the carrier's amplitude would only change the volume of the waveform, not its timbre. Here is the sound generated with a carrier frequency equal to 200 Hz, modulator frequency equal to 400 Hz, and modulator amplitude equal to 800. Here you can see its spectrum. Let's now generate a sound that's twice higher in pitch but has a similar timbre. According to the frequency ratio, RF equals 0.5. In this particular case, it suffices to double the modulation frequency FM to raise the sound by an octave. To preserve the ratio RF, we must double the carrier frequency as well. Here is the resulting sound. And here is its spectrum. You can hear that the octave higher version has a similar timbre and the partials are correctly spaced, yet their amplitudes look a little bit different. Well, that is because we have not changed the modulation amplitude. If we set AM to 1600, so twice the original value, we get the following sound. Here is its spectrum. As you can hear, this last one sounds more like the original. As you can see, the partial structure is completely preserved. They are just spaced apart more because of the higher pitch. Why did we need to change the modulation amplitude as well? Because the amplitude of each partial is determined by both the amplitude and the frequency of modulation. The meaning of the modulation amplitude at modulation frequency equal to 400 Hz is different from its meaning when the modulation frequency is equal to 800 Hz. That's why we need to use a different parameter to control the timbre, the modulation index. It's simply more handy to use the modulation index than the modulation amplitude. Modulation index will change the modulation amplitude according to the current modulator frequency. The formula for the modulation index I is very simple. It's just the modulation amplitude divided by the modulation frequency. We can plug this formula into our simple FM equation. In our previous example, initially we had modulation amplitude equal to 800 and modulation frequency equal to 400, which resulted in modulation index 2. After raising the pitch by an octave, we had modulation amplitude 800 and modulation frequency 800, which resulted in modulation index 1. Thus, our partials amplitudes changed because we had not preserved the modulation index. To remedy this, we doubled the modulation amplitude to 1600 and hence obtain modulation index 2, the same modulation index as the initial sound. The key takeaways are: use modulation index instead of the modulation amplitude to preserve partials amplitudes when changing pitch, and use constant carrier to modulation frequency ratio to preserve partials frequencies. In other words, to preserve the timbre when changing pitch, keep the modulation index I and the carrier to modulator frequency ratio RF fixed. Now, our simple FM diagram looks as follows. Again, a box with a sine symbol inside denotes an oscillator. The plus inside the circle denotes sample-wise signal summation. The asterisk denotes sample-wise multiplication. Since we've just revisited the simple FM equation, let's do one more adjustment to it. If we are less mathematically strict and we attempt to solve the integral in the carrier oscillator's phase, we obtain the following FM equation. Here, AC is the carrier amplitude, FC is the carrier frequency in Hertz, T is time in seconds, I is the modulation index, and FM is the modulator frequency in Hertz. Why do I say that we are less mathematically strict? Well, that's because the signal represents phase modulation, PM, not frequency modulation, FM. What's the difference? That is a great question. Most sources I've seen say that the difference between the two is not relevant and point to just 2 research articles that explain the difference. The answer I found in an article by Frode Holm is that FM and PM are equivalent if the sampling rate is high enough. Then the numerical integration used to implement the FM equation approximates the continuous time integration accurately enough. On the other hand, inaccurate integration, when the sample rate is too low, results in diverging partial amplitudes between FM and PM. Take a look at this example. Here, carrier frequency equals 200 Hz, modulation frequency equals 400 Hz, and modulation index equals pi, so around 3.14. When the sampling rate is equal to 96 kHz, we obtain the following magnitude spectra of PM and FM. As you can see, the spectra nicely overlap. Audibly, there's no difference either. Here is an FM sound at 96 kHz. Here is the corresponding PM at 96 kHz. I can hear no difference. However, if we decrease the sampling rate to 22.05 kHz, the partials amplitudes differ much more. FM has stronger first, second, and fourth partial, while PM has stronger third partial. We can also start hearing a difference between the two sounds. Here is an FM sound at 22.05 kHz. Here is the corresponding PM at 22.05 kHz. To my ear, the FM sound has a more pronounced low-frequency partial. That's, in essence, the difference between FM and PM. At high enough sampling rates, they are equivalent. The lower the sampling rate, the more their partials amplitudes differ. To drive this point home, let's take a look at time domain plots of a carrier at 600 Hz, a modulator at 50 Hz, and the resulting FM and PM signals. As you can see, they are identical. Looking at FM and PM equations, you can tell that implementation-wise, it's way easier to use PM, and that's what we'll do for the remainder of this video. So from now on, our go-to formula for frequency modulation will be the PM formula. This is the formula that we will analyze in the context of FM. So everywhere I say FM, from now on, I refer to PM. Well, it's just like the synth manufacturers, right? So, my wife told me that if I want to have more subscribers to my channel, I should have more cats in my videos. So, here you go. Let's now consider how to control the timbre of FM. We said that if the ratio of the carrier frequency to the modulation frequency, RF, is constant, the pitch will be constant. But what is the pitch in FM? We have two frequencies, carrier frequency and modulator frequency. Which one is the pitch? To answer this, we must answer a different question first. When is FM spectrum harmonic? It turns out that harmonic spectra are obtained only if the ratio of the carrier frequency to the modulator frequency, RF, is rational. So it is a ratio of integer numbers. Let's take a look at a few examples and listen to them. First, let's set the carrier to frequency ratio to 1:2. Here is the resulting sound. Second, let's set the carrier to frequency ratio to 2:1. Here is the resulting sound. As you can hear, since the carrier to modulation frequency ratio is rational, the spectra are harmonic. Now, let's see what happens if we violate this. Let's set the carrier to modulation frequency ratio to the square root of 2:1. As you can hear, as soon as the C to M ratio becomes real but not rational, then the sound becomes metallic and inharmonic, like a detuned sawtooth. Let's listen to an extreme example of C to M equal to 100 to 99. Even here, we still hear a harmonic sound. And that's despite the beating effect caused by inharmonic partials close to the harmonic ones. Apart from the rational ratio requirement, the literature says that if we want to obtain a clearly audible pitch, the numbers in the ratio should be relatively small. Well, what if they aren't small? Let's listen to an example with the C to M ratio equal to 10 to 9. Here, we can hear what happens when the small ratio requirement is neglected. Although the ratio is rational, we have a sense of inharmonicity. The inharmonicity is caused by reflected partials with negative frequencies that are being mirrored back onto the positive frequency axis. Thus, the sound is not as clearly harmonic as in the previous examples with rational RF. The key takeaway is that if you want your FM sound to be harmonic, keep the carrier frequency to modulation frequency ratio rational and relatively small in numerator and denominator. Okay, we know what to do if we want to have a harmonic spectrum of an FM sound. Now, what's the fundamental frequency, the pitch in FM? In general, the fundamental frequency is the difference between the harmonic partials frequencies and is typically the lowest harmonic partial. The pitch is the sensation of the perceived height of a sound and is most often associated with the fundamental frequency. In the following section, I use the two interchangeably. In FM, if the ratio of the carrier frequency to the modulator frequency is rational, then the fundamental frequency F0 can be computed as the carrier frequency divided by the numerator of this ratio, or the modulator frequency divided by the denominator of this ratio. So if you want to generate a sound with a specific carrier to modulator frequency ratio N1 to N2 at pitch F0, you should set the carrier and the modulator frequencies as shown in these equations. That's how I generated the examples we listened to. By setting F0 to 200 Hz, the harmonic examples seem to have the same pitch, although they differ in timbre. As an interesting feature of FM, I will show you that the carrier to modulator frequency ratio, RF, not only allows us to fix the timbre and steer the pitch, but also to eliminate partials. Specifically, if the denominator equals 1, all harmonics are present. Here's an example. If, on the other hand, the denominator is even, the spectrum is odd, so only odd partials are present. Here's an example. Note the missing second, fourth, sixth, and eighth harmonics. Now, if the denominator equals 3, every third harmonic is missing. Here's an example. I hope you start seeing a pattern here. In general, if the carrier to modulator frequency ratio equals N1 to N2 and both N1 and N2 are integers, then every N2th partial is missing. Okay, we now have a sense of what makes FM sounds harmonic and how to control their pitch. How to control the brightness of FM spectra then. The brightness of a sound is typically associated with the presence of high frequencies. In FM synthesis, we can control the center of the sound spectrum with the carrier frequency, the spacing of the partials with the modulator frequency, and the bandwidth of the spectrum with the modulation frequency and the modulation index. If you want to change the bandwidth of the spectrum, resulting in a brightness change, without changing the pitch, we can simply alter the modulation index. Specifically, John Chowning computed the bandwidth of a simple FM sound as 2 times the modulation frequency times the modulation index incremented by 1. By bandwidth, I refer to a frequency range in hertz that encompasses the most significant partials, but not all of the partials. Let's look at some examples using a carrier frequency equal to 1000 Hz and a modulator frequency equal to 200 Hz. Let's set the modulation index to 1. Here is the resulting sound and its spectrum. As you can see, its bandwidth is 2 times 200 Hz times 2 equals 800 Hz. Although there are partials outside this range, they are not significant. Let's now increase the modulation index to 2. Here is the resulting sound. As you can hear and see, the spectrum got wider, and as a result, it sounds brighter. Let's now set the modulation index to 3. And now to 4. As you can hear and see, the spectrum gets so wide that it expands over to negative frequencies. Negative frequencies get reflected back, and hence the spectrum is no longer symmetric. However, it is still harmonic because just the amplitudes of the partials changed after the reflection, not their positions. Finally, let's set the modulation index to 5. This spectrum is clearly the brightest, and it's not symmetric. We could go even further than this, but I leave it for your experimentation. While watching this video, have you noticed how efficient frequency modulation is in generating rich sounds? With just 2 table lookups to get the value of the carrier and the modulator, we are able to generate quite elaborate spectra. With a few simple controls, we are able to change the spectrum in a significant but meaningful way. This low computational effort paired with powerful sonics was the reason why FM was one of the first synthesis techniques, if not the first, to be successfully implemented with digital electronics. In the 1980s, the chips were too weak to efficiently implement the alternatives like additive or subtractive synthesis. If you want to learn how to efficiently generate a sine, or any waveform for that matter, using table lookup, check out my wavetable synthesis explainer video. In the example so far, we could see that the FM spectrum definitely has some pattern to it. Can we accurately predict what the partials amplitudes will be for given parameters? It turns out that we can. As the literature reports, we can write out the PM equation as you can see here. In this equation, sigma is the sum operator. As you can see, it is an infinite sum where each summand corresponds to one integer value assigned to k. Here, each value of k corresponds to one partial. jk of I is a Bessel function of the first kind of order k, whose argument is the modulation index I. The vertical lines denote the absolute value, an operator that removes the negative sign from a value. As before, Fc is the carrier frequency in Hertz, Fm is the modulator frequency in Hertz, and T is time in seconds. Bessel functions are a very important concept in mathematics. They appear in the solution of the wave equation, the basic equation of acoustics. Here's how Bessel functions of the first kind look for orders from 0 to 3. As you can see, they are very similar to sines and decrease in amplitude the higher the absolute value of the argument. You can also observe that Bessel functions of even orders are even, symmetrical with respect to the y-axis, and Bessel functions of odd orders are odd, symmetrical with respect to the origin of the xy plane. What is more important, Bessel functions cross the value of 0 for many values of the argument I. It means that at particular values of the modulation index, some partials with amplitude 0. As you remember, when we increase the modulation index, the spectrum gets wider, but some partials may temporarily disappear. It's hard to get a feeling for the meaning of the partials amplitudes equation without any visuals. Thus, here you can see a plot of how the spectrum changes if we vary the modulation index I in the 0 to 20 range. How to read this plot? Say you want to see how the spectrum looks for a particular value of I, for example 10. Then find 10 on the I-axis on the right and mentally cross-sect the three-dimensional spectrum along the partials axis. This cross-section is your sound's magnitude spectrum at the modulation index 10. The 3D Bessel functions plot gives you the full insight into the spectrum of FM sounds. You can go back to this plot over and over again to discover more and more properties of the FM spectrum. As you can see, it is completely frequency independent. For each fundamental frequency, the partials behave identically. Of course, this plot does not take reflected frequencies into account, but you can visualize them yourself. What we have discussed so far is simple FM. We have one sine carrier and one sine modulator. Simple FM can be extended in various ways to create even more complex sounds. We can add feedback, where the output of an FM instrument modulates the modulator. We can do this for any setup of carriers and modulators, but the most popular approaches use 1, 2, or 3 oscillators within the feedback loop. We can add multiple carriers modulated by the same oscillator. This is called multiple carrier FM, MCFM. It can be used to create formants in the sound spectrum. We can have non-sine carriers or modulators. However, non-sinusoid modulators can result in very dense spectra, so we should be careful when using harmonically rich modulators. We can add multiple modulators, parallel or serial, that modulate one carrier. This is called multiple modulator FM, MMFM. This technique increases the number of partials in the output spectrum. Again, multiple non-sine modulators make little sense because the spectrum gets too dense. We can use oscillators with exponential control, which emulates analog gear. This is called exponential FM. Exponential FM is used in virtual analog applications. We can combine 2 or more FM instruments in parallel or in serial. However, this may quickly get too complicated to control. We can add envelope generators, EGs, to control various FM parameters. For example, an envelope generator controlling the modulation index can create a naturally sounding effect of timbre brightening with the initial transient. An EG-controlled timbre gets darker and darker the longer the sound is played, or a keyboard key is held. Phase distortion, PD synthesis, is another take on phase modulation. In this technique, the modulator frequency is equal to the carrier frequency or to its multiplicity. Moreover, various modulator waveforms are used, for example, a triangle waveform. Ollie Larkin, whom I interviewed in the 15th episode of the Wolf Talk podcast, is well known for his implementations of CAMEO's phase distortion emulations. The discussion of all these extensions is beyond the scope of this already quite long video. Should they be discussed in more detail in future videos? Let me know in the comments. And don't forget to subscribe and turn on notifications to get notified when they appear. In this comprehensive video, you've learned about the frequency modulation FM and phase modulation PM synthesis. You've learned how these two are different, how their spectra look, and how to control these spectra. You've also learned what Bessel functions are and how the partials amplitudes in FM synthesis follow Bessel functions with increasing modulation index. You've learned what the modulation index is and how to use it to control the bandwidth of FM spectra. Finally, we have mentioned various extensions to the simple FM technique. In future videos, we will look into how to implement the PM synthesis technique using various programming languages, so look out for those. Don't forget to check out the full article explaining FM synthesis together with the Python source code used for generating all figures and audio examples on thewolfsound.com. The link is in the description. You can also find there a rich list of books and articles on FM synthesis that I based this video on. Finally, if you want to learn digital signal processing from the ground up to be able to understand all the diagrams, equations, and use them to create awesome audio effects, then check out my DSP Pro online course on learning digital audio signal processing. It's available at wolfsoundacademy.com/DSP-Pro. Once again, it's wolfsoundacademy.com/DSP-Pro. Thanks for watching and see you in the next video. Take care.